Hi students, welcome to class. In lesson 9.4 we will be looking at operations with functions. Well, when we think of operations in mathematics, you probably think of the standard add, subtract, multiply, and divide. And you can perform operations on functions in much the same way that you perform operations on numbers or expressions. You can add them, subtract them, multiply, or divide functions by operating on their rules. So our learning goals are to add, subtract, multiply, and divide functions. So that's our first learning goal, is to actually do these for operations on functions. And then we're going to be learning a new operation called composition of functions. So we will be writing and evaluating composition functions. And then we'll write composite functions and determine restrictions on their domain. So besides adding, subtracting, multiplying, dividing, we're going to be focusing on composition of functions. But we're going to start off with a little bit of notation. So what does it look like when we're asked to add two functions? So sometimes we write addition of functions in this way, where we say f plus g of x, which really means the same as f of x plus g of x. So it can be you'll see it written either of these two ways. So if you had some function f and some function g, and you saw either one of these things asked of you, you know that that would mean they want you to add the functions. Now, subtraction of functions looks very similar. You can write it two different ways, like this, or f of x minus g of x, like this. Both mean to take the two functions and subtract them. Now what about multiplication? So if we kind of followed that pattern, multiplication would look like this. One way to write it is in this way, which really means f of x times g of x. And similarly, that was a tough one to say, we can write division of two functions in two different ways. So when you see this, f over g of x, that means f of x, that function which we call f, divided by g of x. Now, one thing we need to note on division is that g of x, whatever function is the denominator, cannot equal 0. And that's, again, because if you have a denominator of 0, your function is undefined, or the operation is undefined. So the good news about these four operations is we have done addition, subtraction, multiplication, and division of functions before. We just didn't have them maybe written as functions. We maybe just wrote them as some sort of algebraic expression. And so we know when we add and subtract algebraic expressions, we can only add and subtract like terms. But when we multiply and divide, we can multiply and divide anything. So let's take a look at a few examples of those four operations. So let's say f of x is defined as 4x squared plus 3x minus 1, and g of x is defined as 6x plus 2. If I'm asked to add f plus g of x, or another way to say that is f of x plus g of x, then I just simply take f of x and I add to it g of x. And in doing so, I'm going to add my like terms. So let's see. There's just one x squared term, so there's no other x squared. So I have 4x squared. Okay, then I have x terms that I can put together. So if I add 3x and 6x, I get 9x. And then, of course, I have my constant terms of -1 and +2, and those add to +1. So then we could say that f plus g of x was equal to 4x squared plus 9x plus 1. And that would be the sum of those two functions. Okay, so how about subtracting? Well, if you remember when we subtract, whether it be real numbers, algebraic expressions, or whatever, the order that the things that we're subtracting makes a difference. We can't just switch it around like we can addition. And so in this case, we have to see which one's coming first. So it says that we're going to subtract g of x from f of x. So my f of x was 4x squared plus 3x minus 1. And from that, I'm going to subtract g of x, which was 6x plus 2. Now, here I'm going to really stress the importance of parentheses, because remember, when we're subtracting algebraic expressions, or really anything, we can really rewrite this as addition of the opposite. Well, it's the opposite of this entire quantity. So if we took that minus, changed it to plus a negative, and distributed that negative through, and then just rewrote it, then it would be simply addition. And we can just add our like terms together. So if we distributed that negative through, that makes this a negative 6x, and that makes the positive 2 a negative 2. And that way we are sure to subtract both things from the first function. And so when we do, we put our like terms together. We have no other x squared terms, and so we start off our difference between these two functions with 4x squared. Our x terms, we have 3x and a negative 6x, which makes minus 3x. And then our constant terms, negative 1 and negative 2, and we put those together, we get negative 3. And so the difference between f and g, so f minus g of x, is equal to 4x squared minus 3x minus 3. So this probably feels very familiar, and it actually is, because we've spent a lot of time adding and subtracting algebraic expressions, which is really what's just going on here with these functions. Now, how about multiplying and dividing? So this time we're going to redefine our function. So now we're going to use f of x as 6x squared minus x minus 12 and g of x as 2x minus 3. And this first question asks us to multiply them. So if we wanted to find out what f times g of x was, we'd have to take f of x and multiply it by g of x. And we know that when we multiply quantities like that, that means we have to do some distributing. So we could distribute, and you can start with really anything if you want to distribute either direction. I'm going to start off by just distributing and then the minus 3, but you could start with the trinomial and distribute to the binomial if you wanted to. So 6x squared times 2x is 12x cubed, and 2x times minus x is minus 2x squared. And then the 2x times the minus 12, which makes minus 24x. And now we're going to jump over here and start distributing the negative 3 through. So the negative 3 times 16x squared is minus 18x squared. The negative 3 times the negative x is positive 3x. And then finally, the negative 3 times the negative 12 is the plus 36. So as I put my like terms together, there's just one x cubed, so that's 12x cubed. I have a couple of different terms that have x squared. I have a minus 2x squared and a minus 18x squared, so that makes minus 20x squared. My negative 24x and positive 3x come together to give me a negative 21x. And of course, there's only one constant term, and that's 36. And so there is my product of those two functions. And how about dividing? Okay, so dividing the two functions. Well, we've talked about many different ways to divide expressions this year. We've talked about long division, synthetic division, and we even just finished up in the prior chapter with factoring and canceling common terms on numerator and denominator to divide. So if they divided evenly, that's the way that we could do that. Of course, there's also this, like I said, the long division and synthetic division. So if I were dividing 6x squared minus x minus 12 by 2x minus 3, I might start off by trying to see if it's factorable, if I could factor it and see if there's a common term. So I'm going to do the AC method. So I know I multiply the a and the c, and 6 times negative 12 is negative 72. And so I'm looking to split the middle term here up into factors that would multiply to negative 72 and add to negative 1x. And so I could rewrite this like this. 6x squared. I'm thinking negative 9 and positive 8. So negative 9x plus positive 8x minus 12. So now that I have a 4-term polynomial, I can split them up and factor by grouping. And so if I want to factor by grouping, see if I can make some space here. I'm going to take the GCF out of the first pair, so I'm going to look at this first pairing of terms, and I'm going to take out a 3x out of both of those, and when I do, that's going to leave me with a 2x minus 3. And out of the second pairing, I can take a positive 4 out, which leaves me again with a 2x minus 3. And so that means that the numerator factors down into these two binomials, 3x plus 4 and 2x minus 3. Lighten that up a little bit so that helps. And we had a denominator of 2x minus 3, so you can clearly see that the 2x minus 3's are going to cancel, and that means that the quotient between these two functions is just simply 3x plus 4. So the quotient, that quotient between f and g is 3x plus 4, and I just have to make sure I'm very clear that x cannot be equal to whatever would make the denominator equal to 0. And I know that means x cannot be, if I set 2x minus 3 equal to 0, that would come out to be 3/2. So my quotient is 3x plus 4, and x cannot equal 3/2. So there's an example of each of the 4 operations: add, subtract, multiply, and divide. Let's turn the page. So of course on the U-try I'm going to leave you the most difficult ones, because those are the ones that we want to know. If you're going to make errors, these are the most likely places to make the errors, and of course the subtracting and the dividing seem to be the ones that give students most trouble. So I'd like to set C and D as U-try questions. So go ahead and pause the video. Using these new functions, f of x being 5x minus 6 and g of x being x squared minus 5x plus 6, please subtract them in example C and divide them in example D. And then you can turn back in and see how you did. Pause the video now. All right, so thanks for giving that a try. And I'm sorry I forgot to mention that in example D they had 2 new functions. So in D you were supposed to divide the new f of x and the new g of x. So please take a moment and check your work. And other than possibly using the wrong function, hopefully you noticed that, in D, how did you do? Remember, you can always make a note on anything that you're struggling with, and be sure to bring those things up when we meet in class. So one thing to quick note, in the subtraction, notice I changed that to addition of the opposite. I made sure to put g of x second also, and I distributed that negative through and added like terms. In example D, I was sure to list the 2 places that would make the denominator 0, so that would make that quotient of those 2 functions undefined. And you always want to do that before you do any canceling out. So 2 or negative 2 would be values that would be restricted from the domain of that quotient of those 2 functions. Okay, so in the introduction to this lesson, we talked about a 5th operation that we were going to explore, and that operation is called composition of functions. Now, composition of functions is when we use it's another function operation that uses the output from one function as the input for a second function. So what do we mean by composition of functions? And why does it look so much like multiplication? Well, first of all, let's talk about the notation. So composition of functions, 2 functions, f and g, would be notated like this. So that little dot there, the little open dot, not the fill dot that we associated with multiplication, that means composition of functions. And you'll see it written like this with the f and then the open dot g of x, like that. Or you'll see it written like this, f and then in parentheses g of x. And how it's read is, in either case, f of g of x. So it's read just in order, And so what we're saying is we want to know f's value when the input is the function g of x. So again, how this is read is we read that f of g of x. And we want to make sure we are real careful not to confuse this with multiplication. So that's why we talked quite in depth about what the notation looked like earlier for all the other operations. So when we got to composite, we know that you'll see it either written like this with the open dot, or you'll see it written with nested parentheses. And in both cases, that's indicative of composition of functions, and it's read f of g of x. Let's turn the page and take a look at what is composition of functions. So I mentioned that composition was a kind of operation that uses the output from one function as the input for a second function. So the first thing we're going to do is look at evaluating for specific input of x. So it says use order of operations for these expressions, and they want us to find f of g of 3. Well, if we were asked to find f of g of 3, we would evaluate the g of 3 first. So what you do is you work inside the parentheses, and then whatever you got for a value, then you would substitute that into the other function f. So here's an example. So I have two functions. F of x is 2 to the x power, and g of x is 7 minus x. And they want us to find, in example A, f of g of 4. So when I think about this, and I think about f of g of 4, if I didn't know what was in the parentheses, let's say this was missing here, this wasn't there. Normally what you see in there is a value, like a specific value, number, some sort of, integer, or maybe even a fraction or decimal, and if you see that f of that number, it's saying take that number and substitute it into the function f. Well, because this time it's not a number, what it's saying is take the value of whatever we get here, of the value of g of 4, and substitute it in for f. So the first thing would be to find g of 4. So g of 4 means I'm going to take 4 and I'm going to plug it into this function right there. So I'm going to plug that in wherever I see x, and that would look like this, 7 minus 4, and that would give me an output of 3. So then what I would do is I would take that value and plug it in to f. So now I'm plugging 3 in where I see x in the function f of x. And so that would be in the position of the exponent. And so that would give me 2 to the third power, or 8. And that means that f of g of 4, the final value is 8. So far that seems easy enough. And how about if we designate example B as a U try? I walk you through here with telling you what to do for step 1 and for step 2. And by the time you get to the end of step 2, you'll have the value of the composition function. Now notice we have new functions. F of x is now 2x minus 3, and g of x is x squared. So please pause the video now and give example B a try. Okay, so in this case, this example, also notice that the functions were switched around. This time, they asked you to find g of f of x. So this time we wanted to take our value of 3 and substitute it into f, and then whatever we got for an output there, we took that output and put it into the other function. And so composition of functions is like combining functions in a specific order, and the order has to do with which is the innermost function, the nested parentheses. So we start on the inside and we work our way out. And so it's like we're layering one function after another. The output of the first function becomes the input of the second. It's almost like a kind of like a chain link, like a chain reaction. F of 3 gives us an output of 3 in this case. Then we take that 3 and plug it into the next function, and the final output is 9. So the result of the chain reaction is 9. But what about composition of functions in general? Not with a specific input value like 3 or 4 or negative 5 or whatever, but in general composition of functions if we wanted to combine functions in this way. similarly to how we added them or subtracted them or whatever. Like for instance in this next example, if we are given that f of x is equal to x squared minus 1, so this is our first function, x squared minus 1, and g of x is one of these rational functions, x over 1 minus x, and we're asked to write each composition function and state the domain of each. Well, so one thing to note real quick before we do this, the domain, when we talk about domain, remember that means inputs. The domain of a composite function depends on the inner function and the outer function as well, or the final function that we get. So when we think about some kind of functions that have maybe asymptotes, places where the graph can be undefined, maybe values of x where the function doesn't work, like when we're doing square roots of negatives, things like that. We have to kind of keep in mind what the two different functions that we're working with under the composition of functions. So what does this mean, f of g of x? What does that really mean? What that means is, like if I had this covered up, this g of x, then say this wasn't here, white it out, then what we usually think of, what's in the parentheses after that function, is we're saying whatever's in the parentheses is what I'm going to take and plug in for x for that function. Well, that's exactly what it means here. It means we're going to take this function, g of x, which happens to be x over 1 minus x, and we're going to take it and we're going to plug it in right here for x. We're going to plug it in the other function. And if we did that, this is what it would look like. We would be plugging it in and squaring it. So we just took that function and I took out where x was, and I'm going to put in place of it x over 1 minus x. So the composition of f of g of x is the quantity x over 1 minus x squared minus 1. But we need to simplify this. Well, I'd have to start off with the squared. So I have that quantity being squared, which means I could square the numerator and make that x squared, and I could square the denominator, which makes that 1 minus x squared minus 1. But then in order to simplify and put those together, I need a common denominator. So in order to get a common denominator, I'm going to have to come over here to that minus 1, and I'm going to have to make sure it has a denominator of 1 minus x quantity squared. And so I'm going to multiply the top and the bottom of that fraction 1 over 1 by the denominator of the other one, which was the 1 minus x squared. Then that way, it will have the same denominator. Now there's really no need to expand out that 1 minus x by using FOIL or anything, because we can see that, what the common denominator is going to be. And so that turns into, well, we have the first term, which was x squared over 1 minus x squared. But now we have minus 1 minus x squared over 1 minus x squared. And if we then expanded out just the numerator, the denominator is fine. We don't really need to expand that out. But if we took this 1 minus x and we squared it, and I'll just do that here off to the side. So that really means 1 minus x times 1 minus x. So I'm going to FOIL this. 1 times 1, which is the first two, that's just 1. Outside 2 minus x, inside 2 minus x. Last two, negative x times negative x is positive x squared. If I turned that around and wrote it in descending order of powers and put like terms together, it would be x squared minus 2x plus 1. And so that's really what this numerator is, and I can rewrite that as x squared minus 2x plus 1. But now that we have like denominators, we can add our like terms on the numerator. And our denominator will just be that 1 minus x squared. Putting the like terms together on the top, first of all, I want to change this to plus a negative, so I'm going to have to take the opposite of everything in those parentheses. And so I have an x squared, and I can subtract x squared, which they just cancel each other out. If we put the x squareds together and subtract them. So then I have the negative. I'm going to distribute through to both the negative 2x, which makes positive 2x, and the positive 1, which makes minus 1. And so my final composite of those two functions is this 2x minus 1 over 1 minus x squared. Now remember that when we have a denominator that has a variable in it, there's always the potential that there's going to be a place where that function will be undefined. And in this case, what will make the denominator undefined is 1. So we would have to restrict that from the domain. So we'd say that the domain of f of g of x, x cannot equal 1. And that's because it's going to make the denominator undefined. It's going to make g of 1 will be undefined, so that'll make the denominator undefined. So there's our first look at composition of functions. Let's turn the page and look at a few more examples. In this next example, we're going to use the functions f of x is equal to 3x minus 4, and g of x is equal to the square root of x plus 2. And in each case, we're going to write the composite function and state the domain of each. So in the last example, we just did composition of just one direction. We did the composition f of g of x. Now this time, we're going to show both directions. And you know how multiplication and addition, they're commutative. It doesn't really matter which order you do things in. Well, what we want to do through this example is see, is composition commutative? Because in that last example, we got the final answer, but what if we had done it in the different order? What if instead of asking for f of g of x, we had asked for g of f of x? Would we have gotten a different answer? Well, let's take a look at it in the context of this next example. So let's see, g of f of x. What this is saying is, so this first one is saying take f of x, this function right here, and wherever you see x in the other function, so there it is, substitute in 3x minus 4. So here's that general format of the function. It looks like this. And where x was, now I'm going to put in place of it 3x minus 4. So again, we started off with the function that was inside the most nested parentheses, f of x, and we took that function and substituted it into the outer function, which was g of x. And we ended up with this, the square root of 3x minus 4 plus 2. Well, now there's nothing really to do that we can do to simplify this any further, unlike in that last example. So really the only thing we can do is just rewrite this, and that will be our answer. Our g of f of x is just square root of 3x minus 4 plus 2. So what about the domain? Well, if we think about this final function, and we also think about the input. So, when we took that 3x minus 4, and we think about that, there was really no restrictions on that at all. That's a linear function. There's no reason we can't plug in just anything we want in for x, because then we're going to multiply it by 3 and subtract 4. Lines, no problems with the domain, all real numbers. But then the function we actually plugged that into was a square root function. And remember that when we take an even root, we only get even roots for real positive numbers or 0. So numbers that are greater than or equal to 0. And so when we think about that final function, square root of 3x minus 4 plus 2, the part that's here underneath the radical, we know that that part cannot be anything lower than 0. So we know that that 3x minus 4 has to be greater than or equal to 0, and we can find this restriction on this domain by just solving this by adding 4 to both sides. And that leaves us with 3x is greater than or equal to 4, and then divide by 3. And so we could say that our domain would have to be x must be greater than or equal to 4/3. So that's going to be a way to qualify our composite function. We have to say this is the function, except for we have to keep and make sure that x must be greater than or equal to 4/3. Well, how about if we went the other way? So if we went the other way, then we would be saying this. That means we're saying we want to take g of x, that function, and plug it into the function f. So that means we're going to take this whole function, square root of x plus 2, and we're going to plug it in for x there. So what that's going to look like is this, 3 times, and in that spot where x was, we're going to place, in place of it, that other function, the square root of x plus 2. Now, with this particular function, we can simplify just a little bit. We could distribute that 3 through, so I could just go ahead and distribute that 3 to the square root of x and the 3 to the 2, and that would make the 3 times the square root of x plus 6, and then minus 4, and then I could put my like terms together. So 3 times the square root of x plus 2 would be my final composite function. So notice those are different. They're not the same function. So we said we were going to ask the question, is composition of function commutative? And it's not. So composition, the order makes a difference. The order that you do them, and kind of like with subtraction and division, the order that you divide things in makes a difference. The order things that you subtract things in makes a difference. Composition is just one of those functions that is not commutative. The order makes a difference, so we have to make sure we start with the innermost function and work our way out. So how about a domain for this particular one? So when you think about the input, the g of x, that thing that we put in, it was square root of x plus 2. Well, the one thing that we have to be careful of with square root functions, we have to have numbers that are greater than or equal to 0 under our radical. So it's just an x under there. That means the x has to be greater than or equal to 0. And if you look at the final function, that is the case here too. I mean, this x under the radical can't be negative. So we just have to make sure that we classify or clarify that and say that the x must be greater than or equal to 0. So that would be our domain, would be x has to be greater than or equal to 0. So that goes along with that composite function. So our final example is an application, a real life problem, if you will. So we're going to leave this one for in class. So this is where we'll pick up when we meet again in class. So I'll see you then.